Hello, everybody. Good evening. I hope you can hear me all right. I will start sharing my screen and it should be up in a minute. Okay. All right. So, welcome everybody to the 8th session for the course Essentials of Data Science with R Software. So we are done with 7 sessions, and I believe now all of you are familiar with how it's going on. Right. So before we start the session, do you have anything to ask or suggest or discuss? So we'll start off with what was covered in this week. And we will be doing a little bit of integration today, a little bit more in detail. I would mostly be doing the same questions that were there in the lectures or the same ones which are there in your assignments, very similar to those. Ahead of that, like we discussed last time, within the next couple of weeks, I will discuss it with the other TAs and send over a list of basic or important integration formulas that you can remember, so that if you do get those questions in exam, you should be able to solve those. Other than that, do you have anything to ask? And like always, feel free to message in the chat, or you can directly unmute yourselves and ask throughout the session. So I'll just give you sort of a disclaimer. I had maths in school in 11th and 12th, so I am familiar with integration, but it's been a while since I've solved little bit difficult questions of integration. So I do have, sorry, say that again. Anything? Did I start the recording? I did, right? One second. Let me check. Yeah, the recording is on. Okay, were you saying something? Okay, never mind. Fine. So, okay, you should be able to see the screen now. Fine. So, so as I was saying, please let me know in case I'm stuck somewhere or if I'm doing any of the calculations incorrectly. Right. So let's start. And yeah, okay. So this week was mainly talking about two concepts. The first one being bivariate distributions. So in the previous weeks, the different kinds of distributions that we
Ma'am, hello.
Yeah.
Ma'am, week 7 assignment, 8th and 9th problem, can you solve, ma'am?
We will get to it towards the end of this session, okay?
Okay.
Right, so question 7 and 8. Let's try. I will take a look at it at the end.
8 and 9, ma'am. 8 and 9. 8
Oh,
and
8 and 9. Okay, fine. 8 and 9 from assignment 7. Okay, fine. All right. Yeah. So until now, until the previous weeks, what we had seen was that you have an input and you get an output, basically, right? Now there are going to be two things that you're inputting and you get an output in terms of the probability distribution. So that probability is based on both the things. Both of them may be independent of each other or they may be controlled by one another, right? And this sort of a distribution, this sort of an arrangement can be there for both discrete random variables and continuous random variables. So again, the terminologies and the nomenclature here, it's going to be that you'll have X and Y as the random variables. And then we will see how are they distributed. So final function. So what is their probability in terms of X and Y? And we will see why it's important to consider, like, ultimately the expression that you're going to evaluate. Sometimes it may contain both X and Y. Sometimes it may contain just one of them. But either way, so it's not just limited to one random variable now. All right. So so now you can evaluate probabilities in terms of one only or in both of them. So basically what I'm trying to say is the range that you're not now talking about, there are two ranges. Let's say you're saying x is between minus infinity and infinity, and y is also between minus infinity and infinity, and you have some distribution. So earlier we were drawing the the probability mass distribution function in a 2D axis. So the x-axis there denoted your random variable, and the y-axis was denoting the output or the probability in that case, right? Or the area under that curve was denoting the probability in terms of continuous. So the y, now what happens is the x and y axis, they are both random variables, and the z axis, so as to say, either for discrete random variables, that is going to be directly your probabilities, or when you have that x and y, and when you find out the volume now of that 3D figure, that is going to give you the probability. But of course, doing that, extending beyond 2D is not possible. It doesn't help us, especially because we don't normally make 3D figures either on computer or on pen and paper. So we don't go into graphical demonstrations now. We'll just go with the formulas. Okay, so fine. So first of all, there are a few different ways in which you can denote the same thing. So first of all, you have the probability, whether you're talking about the mass distribution or the density function. So now since you're inputting x and y, the final probability that we'll denote by a small f, it is in terms of both x and y, right? So this is how you're denoting it. And for random variables, we would more be talking about the probability at a certain point, right? That is mostly when you're talking about probabilities. For random variables, point probabilities make sense, right? So this is how you're going to denote. So probability at a point, not just x is equal to something, but y is equal to something as well. So you're talking about one single point in that 3D space, right? So x is one axis, y is one axis, and this output is going to be a third axis in that sense. And now these are discrete random variables. So x can take any value 1, 2, 3, 4 until I. J can take any values 1, 2, 3, 4 until j. Now the important part here, just to remember, it might not appear very intuitive, but so the length or the number of elements in x and the number of values that y can take, they need not be the same. It's not necessary that they are paired observations. Okay. So this is how we can denote number of x need not be equal to number of y. It may or may not be. You will also see that in some of the questions. So this I and j, basically, they need not be same. Okay. All right. I'll just write that also explicitly here. So I is not equal to j. They may be equal, but it's not necessary that they will be equal. Okay. And then, of course, so this was probability at a certain point. Now, probability up to a certain point, that is how we are defining cumulative distribution functions. And cumulative distribution functions, they make sense for both discrete and continuous random variables. But so for discrete random variable, it would still be in a similar way, the probability x less than equal to xi or y less than equal to yi. But I've just given it in terms of the continuous random variable. So x, the value being small x, and the y value being small y. So now you're going to integrate it. So this is how we'll write it. The function here, the original function, the PMF or the PDF, in this case, it's going to be PDF, that you write. And now you're integrating both. You're integrating in terms of x and you're integrating in terms of y. And the limit, both limits, unless something is given, both limits are going to be minus infinity to plus infinity. But here we have the limit that x is less than x, y is less than y. So these are going to be your limits. We will see in some of the questions how you have to solve it. Sometimes it would not matter which integration you solve first, but sometimes it may matter. Okay. All right. And just it's a good practice. So whichever integration you write here, so you have an outer integration and inner integration. So this inner one is going to be with this, and the outer one here is going to be like this. Just for simplicity sake, just to understand better. Okay. All right. Then when you want to talk, say if two events, if two different distributions, if they are independent. So again, we go to the same definition. The probability of two events occurring together. So like there we used to write it in terms of intersection. So probability A intersection B, if it's equal to probability of A into probability of B, then you would say they are independent, right? But now in terms of you can solve it, you can say this in terms of PDF. So this is in terms of the PDF for a continuous distribution. This is in terms of PMF for a discrete distribution, and this is CDF, again applicable to both. All right, so are we good until here? Any questions, any doubt? So now we are going to build up on these notations, right? So remember, small f, when it's written with x and y both, that means it's just the distribution that we're talking about, the PDF or the PMF. And the CDF also with a capital F, again, we're talking about the distribution in terms of both x and y. We have not fixed any of the values, so you can expect to see both the variables. You may or may not see them sometimes, because if you remember, say, in terms of the uniform distribution, right? That's also a distribution of x, but you never saw the values. You only saw numbers there, right? Because those uniform distribution, let's say if it's between 5 and 20, it's a fixed value, 1 upon 15 or something like that, right? So you may or may not see both variables in the expression for the probability, but typically you would see. Okay, fine. So now we move on to one step ahead. First, we talk about discrete random variables. Okay, now the things that we are going to discuss here for each of the two types of random variables is marginal and conditional probabilities. So what? So by default, the probabilities which consider both variables is joint probability. As the name suggests, you're considering both of them. So it's a joint distribution. But now sometimes it may be possible that you want to say, okay, I'm going to fix a particular value. Either I'm going to fix the value of x or I'm going to fix the value of y. And once I do that, what is the probability remaining? Initially, your probability was dependent on both. But now you're fixing one of them. So you're sort of converting it into a univariate distribution. But that is what we call as the marginal probability. So I have used a color scheme here. So the first line here, it's in red. And this one here is saying that probability x is equal to xi, or it's just written as probability. Now the subscript here is x inside. So the subscript here is indicating that this is the marginal probability, right? In terms of x, right? And you are saying it's going to be x. You can have a certain value of x if you want, but you're not interested in any value of y. So what is happening? You are integrating over, not integrating, you're summing over all values of y. Okay. So this means now initially your probability was in terms of x and y. You could put any value of x and any value of y. Now you just want that I am not interested in values of y. So what you can do is you can sum up all the values. You can say, okay, let's take all possible values. And then at particular value of x, once you fix a particular value of x, you get some output. Once you fix it to another value, you get another output. We'll just see some example in 1 minute. So just bear with me. Likewise, when you talk about the other marginal probability, when you want to fix a particular value of y only, then you're not interested in what values x takes, you sum up all values of x, right? So again, x is written before y, I is going to be written before j, And since you're summing up over all values of y, which is going to be from 1 to j, 1 to capital J. So you basically just make a plus sign here, integrate. It's indicating that you've used up all values. Okay. So once we are done with this, now we might want to find some conditional probabilities. Okay. So what is happening here is, again, the conditional probability of x when y is given to you. So you're fixing y. Now, when you're fixing y, you automatically go here. So given that y is this, so you have fixed y. If you remember from the original definition of conditional probability, the numerator was when both events are occurring. So when it was A given B, it was A intersection B in the numerator and B in the denominator, right? So this part, the right half here is both becomes your denominator, and this one right here becomes your numerator. And this one is nothing but the original function. Okay. The original function, and maybe you would like to put in whatever value of x you're interested in. Is it equivalent to, say that again? Which RHS I would, there are the third one, this thing? Like, yeah. Okay. So, right. So what we are doing here is we want to calculate the probability of x when we are fixing a certain value of y. Okay. Given y is this value, what are the different values? What are the different probabilities of x at different, what are the different probabilities when x is some different values, right? So when you're saying it's given, so it's one step after this. So this was the probability that you can have all possible values of y, right? Until here. Here you have not considered any value of x. Now here in the third statement, you are interested in now when there is a particular value of x. So you have considered all values of y, that's first step. And then you consider some value of x here. So that you're going to fit in the numerator. This value gets fit in later. Yeah, I might have, this I think is incorrect. Let me check. Still confused? Do you want to, can you unmute yourself and maybe ask? Okay, wait, let's take some examples, right? So let's take some examples here. Mic is not, that's okay. All right, no problem. So let's try and solve some things here. So I hope there's enough space, otherwise we'll take a new slide here. Okay. Yeah, all right, fine. So again, I am mostly using the same examples that were discussed in the lectures because they themselves are quite lengthy to solve. All right, so this is a distribution. It's a probability distribution. So first of all, this is a discrete distribution. So we'll have some fixed values of x and y. So x can take values 1, 2, and 3. Y can take values 1 and 2. All right. Now imagine you are in a 3D space, x-axis, y-axis, and the z-axis. So you have the x-axis values here, you have the y-axis values here, and the whatever, once you solve this expression, you can get the z-axis corresponding to it, and that you can plot. So basically, you're going to have some points in that 3D space. This is how it's going to look, but we are not going there. So first of all, what does the first expression ask? So it's asking you what is the marginal probability of x. That means we are not interested in any particular values of y. We'll take the whole range of y. Okay. So first of all, whole range of y. This is what we are doing here, right? So the whole range of y is this 1 and 2, right? And if you see this expression, this was summing up. So what we'll do is we will first fit in, like we'll write x plus, now y here, first value is 1 divided by 21. And then we'll sum up the other option. So x plus 2 divided by 21, right? If you solve this, you're going to get 2x plus 3 divided by 21. Okay. So now what does this tell you? That this, okay, now see, this expression becomes very similar to a univariate distribution. It is a distribution in terms of x. This is what the subscript is showing you. And the capital X here is telling you that you can substitute values of x. So you remember we used to say, find the probability at x is equal to 2, right? X can take these three values, 1, 2, and 3. What is the probability at x is equal to 2? So you put in this value of x here. Here you'll write px, x is equal to 2. You'll put in the value 2 here, and you'll get some value. That's going to be your probability. So this here just indicates it is a distribution in terms of x, and you can fix values of x to get particular probabilities at particular values. Now you are doing away with y. Okay? Right? Yep. 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 Like x is equal to 1, x is equal to 2, x is equal to 3. Okay? Fine. All right. Great. Good. Now you can do the same thing here as well. All right. So would any of you like to solve it with me, or if you can solve it, if yeah, it's nice if you can have a pen and paper handy, right? Otherwise I'm solving it. Just see along. So now I don't want x in my equation. So I'm going to use all values of x. I'm integrating over x here. So it's going to be 1 plus y by 21 plus 2 plus y by 21 and 3 plus y by 21. That's going to give me 6 plus 3y by 21. Okay. So that's the marginal probability of x and marginal probability of y. Okay. This is one step. Now, what is this? The third expression, what does this ask? So it's asking you that when you are fixing, when you're saying that, when you're saying that y here is fixed. Okay. Yeah. So you're fixing some value of y. You're not interested in what the value of x was. You're just fixing some value of y. So that automatically indicates, since you were not interested in the value of x and only a particular value of y, maybe this is what you're interested in. Not maybe. This is what you're interested in. And then you fix a certain value of x. So in conditional probability, you have two events, right? First, you have a given event. This has occurred. And then you're talking about now, what's the probability? So given that you are talking about the whole range, you summed up over all the x's, what's the probability of a particular value of x? Okay. I don't think I can explain this any better. So just it's step 1, 2, 3. The given y is equal to y indicates that you have summed up over all values of x. You're not interested in values of x, and then you are looking at particular value of x. Yeah. How to speak of it? Okay. I don't know how to speak about it, but
Ma'am, please repeat this.
okay. I am writing the expression again. Oh, how to, okay. So this is x given. What is the probability of a certain value of x given y is equal to y? So this right here is going to be, so, okay, wait, this is going to be your probability xy given probability in terms of y. Okay. So probability xy here is your original expression. Nothing fancy about that. 21. And now this is your marginal probability. So this was 6 plus 3y divided by 21. Right? So another way that you can think of this is when you in conditional probability, when you had A given B, the numerator was A intersection B, right? So now the expression is in both terms. It's x and y are here, it's the
Ma'am,
subscript, right?
it means probability of joint events upon marginal probability.
Yep,
This means
yep. That's a very good way to put it. True.
okay.
So yes. So, and why is it joint probability? Because remember there we had intersection. So now instead of intersection, it's like, yes, you're considering both x and y here. So this brings you to the actual original expression. And here given y. So now you're only interested in terms of y, not looking at what value of x occurred. So you calculated the marginal probability in terms of y. Right? Now, likewise, can you tell me what this one would be? What would be the numerator here? Right? And then you can obviously simplify this. So 21 get cancelled. It's going to be x plus y by 6 plus 3y, right?
Numerator will be same and
Right.
denominator will be uh, py marginal probability of py.
Yep. 2x plus 3.
So,
I mean,
yes.
there was denominator 21 in both of them, so that gets cancelled. Right? So, okay. So if this is slightly clear, then we'll move on to the next bit. Okay. I hope it's making sense. It's not all confusing. Yeah. Okay, fine. So the next things that we can do is expectation. Okay. So again, we had these 4 parameters that we calculated in the last slide.
Ma'am, it is more better if you provide us a practice question corresponding to this concept. So it will be a better understanding.
Okay. I do have some questions like this in the upcoming slides. In case if you feel at the end of the session those are not enough and your assignment questions are also not enough, then we can talk about more questions. Okay. Because the questions would pretty much look like this. If you have taken a look at the assignment, this is very similar to what you're going to see.
Okay.
But anyway, let's go ahead and see how it spans out.
Okay.
All right. So again, we calculated these 4 values, right? Now, so the first 2 are relatively, you can think of in terms of that you now got your univariate distribution. Okay. You've summed up over the other variable. You're not interested in how the other variable was affecting your probability. So you're only looking at one particular variable, right? Remember, you had normal distribution in terms of x. So you had x in the expression, or you had Poisson distribution or whatever. You would normally have that variable in the distribution, right? So this is how you are getting these values also in terms of x, this one in terms of y, and the joint probability that's going to be in both of them. Fine. And this is also the conditional probability also. We just saw what it means. Now there are 2 sorts of expectation values that you can calculate. So first of all, expectation of x. Now, if you remember the expectation value for anything, go to the basics, think about the dice, the roll of a dice thing. What is the expectation of the face on the top of that dice? So it's 1, 2, 3, 4, 5, 6. You get the center value because all of them have the same probabilities. But what is the formula that we use? We say 1 into 1 by 6 plus 2 into 1 by 6, so on and so forth until 6 into 1 by 6. So we are summing up the number, the output or the value of that random variable into its corresponding probability. So now this expression on the left, expectation of x, you're just not interested in what is y doing, right? So the random variable is going to be x. The probability is also going to be in terms of x. So that's it. It becomes a very normal looking expression. Likewise, you can calculate the expectation of y. Okay. So this is the expression. This is the formula. Likewise, we calculated these things previously. So now we are interested in the expression of x when y was given to be something. So again, since it's the expectation of x, I think I should just change it. Give me a second. I just copy pasted the formula. So I did not make the edit. Yeah, this should be okay. All right. So, yeah, right. So expectation of, again, the same thing. Again, you're talking about in terms of x, right? This thing. So it's going to be x. Here, it's going to be y. Okay. So let's take a look at some examples again. So the same formula, the same probability distribution, using the same expression. Can you think what would this be? How should we go about it? We're using this formula right here, okay?
Ma'am, summation of 1 into pxx plus
So this one, right? This thing. 2x plus 3 by 21.
Yes, yes.
Right? Okay.
Then plus.
So this is going to be 1 into 2x plus 3 by 21.
Yes, plus 2.
Oh, this is going to be 1, right? Yeah. Oh, wait, let me just mess it up. Okay. Okay. So this one, let me solve here. It's going to be 1 into 2 plus 3 by 21. Then for the second value, which is 2.
Yes.
2 into 4 plus 3 by 21. Then 3 into 6 plus 3 by 21. Right, now you solve this, you get 5 by 21 plus 12, 24 by 21 plus 18 into 3. How much is, sorry, 9 into 3. 27 by 21. Right, so this is 41, 46 by 21. Yep, that's right. Okay. So that's it. Okay, so this is one part. Now for the second bit, it's going to be you're fixing some value of y. Right? So now if you remember this expression here, this one, x plus y by, so this was x plus y upon 6 plus 3y. Right? So this one, we had seen this was 2x plus 3 by 21. And this was x plus y divided by 6 plus 3y. Do you want me to repeat expectation of x again? Okay, fine. So if you remember the expectation of x original calculation, like forget this complicated bit. Expectation of any number is something like a mean. Okay. How much marks do you expect in general? What number do you expect on the roll of that dice? it's going to be something like the mean. It's very different from the mean. It's a different funda, but you can think of it like that value. And how do you get it? The original formulas, if you look at the previous lectures, if you look at the previous slides, it is the random variable into its probability, and you sum up over all possible such values. Weighted average, perfect. That's the exact thing what it is. And this is how you do a weighted average, right? The value into its corresponding probability. You do that for all values. So here we are talking about x. X is our main character here. So we are not interested in what value of y was. So we are summing up over all values of y, right? This is what we did in the marginal probability of x, right? Confused about the expression. Okay, right? So since we were not interested in what value of y is, we'll take all values of y. And this is where we took all values of y, where we calculated the marginal probability of x. So x into its marginal probability, simple. And you sum up over all things. So this is what we had calculated in the previous slide. It's 2x plus 3 by 21. So now you're summing up over values of x, right? So you'll take x1 and x is equal to 2, x is equal to 3, and this is what we are solving here. And this is what we'll get. 46 by 21, which is 2 point something. So it's sort of in this range, right? So that's important. Okay. All right. So that's the first part. Now the second part of the question asks, again, expectation of x, but when you're fixing a certain value of y. And initially, if you remember, this is how we had fixed a certain value of y, right? This y here that we calculated in the last one, it could be for any value of y. We're not, right? You can fix at a particular value. So in this part, they're asking when value of y is fixed at 2, what will be the expectation of x? Okay. So here what we are going to do, first of all, the first step that we are going to do is instead of y, we'll write 2. It's going to be x plus 2 divided by 12. Okay. And now we'll again sum this thing, just like we did here. So it's going to be 1 into, this is going to be 3 by 12 plus 2 into 4 by 12 plus, let's say 3 into 5 by 12. So 12 becomes the denominator. It's going to be 3 plus 8, that's 11, plus 15, 11, 15, 26. That you can write as 13 by 6. Was this clear? Would you like me to explain it again? Understood? Okay, good. Yeah, perfect. All right, good going. So now we have sort of had 8 expressions with us, right? We've not explicitly calculated the last two here, this one expression of y and expectation of y with a certain value of x, but you can sort of appreciate how it's going to be. Okay, we had 4 expressions here and 4 expressions here. Okay, fine. So we do the same thing, but now instead of discrete, we'll have continuous random variables. So instead of summations, we will have integrations. Okay, here I am just telling the formulas, right? So now, so here what we are doing is, again, the expression, we are summing up or integrating all the y's. So here, the y that I've written here, it's not telling you it's going to be till y. This one just here means that we are integrating whatever the value is going to be. Okay, this could be any other value also. So just be a little mindful of the limits that I've written here. But so it's going to be whatever values of y it can take. Likewise, here you have the marginal probability of y. So we'll sum up or integrate over the whole range of x. So whatever the range of x it can take. Okay. Once you have the marginal probabilities, we can also have the marginal joint, marginal cumulative probabilities. Okay. So now this one, small f x of x, this is in terms of x, right? This is what the bracket or the subscript here is indicating. Now, what we can do is we can integrate it up to a certain value also. Up to a certain value of x. So this would typically give you, so this would be, the expression would be in terms of x. This would be in terms of y. This should be a value. We'll just see another example in a minute, but you'll see that. And then again, this is again your
Ma'am,
conditional.
in case of fx, the limits will be minus infinity to y in case of x, because we get the terms in terms of x. We get our answer in
Yep.
terms of x.
So that's what I was trying to tell you here. Here it's going to be, so what I mean by these limits actually is all y, right? And this thing here, it means all of x, whatever values x can take.
We want to, ma'am,
Yep.
we want to remove the function of y so that we have to give y limit in function of x.
Yep.
So
So that's what we are doing.
Yeah.
See, you
Limit
can,
is given as limit is given as minus infinity to y. That is
so
the
it's
problem.
not, yeah. So I was not sure of how to denote it. So it's all the values of y.
Okay.
Let's go to the example in just a minute, and then we'll see.
You
You're
can
right.
write y equal to function of x. Minus infinity to y, that is equal to function of x. Then only you will get entire thing will become function of x.
Yep. You're right.
Y
Fine.
equal to function of x, it may be constant also, no problem.
Okay. I get your point. Fine. We'll just see the example so that we're all on the same page. And so this one again, if you remember, so we had these marginal probabilities, and then from the marginal probabilities, we can also go to conditional probabilities. Again, the same thing. So let's take some examples again and see how we are doing that. So again, it's going to be a little bit, I think the solution would be a little bit longer. So we'll see if we have to go to the next page. But okay, so let's start. So now here you see there is neither x nor y in this expression, right? But doesn't matter, it's still a probability distribution. So the first thing here is f of x, we are integrating over the whole range of y. So the important bit in such questions is that the range of y here is actually between the immediate things that it's there on the left and right. Okay, so here what we are going to write, we are going to integrate 2. Again, we want x in the expression, so we will integrate in terms of y. So the d is going to be dy here. And the ranges of y that it takes, it's going to be between x and 1.
And if you draw a diagram, you will get a good idea.
If I draw a diagram, I don't know if I can draw a
y
diagram
equal to
for
x,
this.
y equal to x, y equal to x line.
This line.
Yeah. Your region is what is that?
Okay, I see.
That
Okay,
region.
so let's say
X
this is x, this is y. So y has to be
Yeah.
greater than x in all
Yeah.
cases.
Upper,
So it's
upper,
going to be the upper, this thing.
Yeah.
Okay, good point. Okay.
Yeah, this region only you want to calculate.
All right. Okay.
And that you have to get.
Okay. Fine. All right. Cool. Good. That's a good point of looking at it. So in terms of the formula, this is what we're going to solve, right? So 2 is a constant that can go out. So the integration, so if you do integral dy, it just gives you y. So this is one of the basic integrations. It's going to be 2 and y, and the range here is between x and 1. So it's going to be 2, 1 minus x. That's it. Cannot solve it any further, right? We have got the expression in terms of x. Right? Now, can any of you tell me how do I solve to get the marginal probability of y? What are my limits?
Ma'am, 0 to y limit
Huh.
to dx.
Okay, perfect. Again, it's going to be 2. It's going to be x here. It's going to be between 0 and y. So it's just going to be 2y. Right? Okay. Good. Okay.
Yes, ma'am. Yes, ma'am.
All right. So we have got in terms of x. We've got this in terms of y. Now we want to do the next part. So we also want to calculate the sort of, it's going to be your cumulative distribution at x is equal to 0.5. So at x 0.5, as you showed here, we are interested in, let's say, what color do I do it with? Maybe this one. So at x is equal to 0.5, we are interested in everything less than that, right? So this shaded part. So, but anyway, right now let's go for the formulas. So here we already have this expression in terms of x. We want to integrate it from whatever the ranges make sense, right? So here the expression is going to be 2, 1 minus x. Now this is in terms of x. So we will integrate in terms of x. And now the limits, we want it at 0.5. So this is going to be 0.5. And the minimum value x can take is 0. Right? So it's going to be this. Okay. Now, okay, let me see if I can do this here. So we'll have two integrals. It's going to be 2 from 0 to 0.5 dx minus, let's say 2 here and 0 to 0.5 x dx. Right? Correct me if I'm wrong anywhere. And then, so again, dx will give you x as the integral. This is going to be 0 and 0.5. Yeah. Okay. I don't have the answers for this. So yeah. Anyway, so x dx gives you x square by 2. So this 2 and 2 can get cancelled. It's going to be x square between 0 and 0.5. And then you can solve. So 0.5 minus 0 into 2, that's 1. Minus 0.5 square, that's going to be 0.25. It's going to be 0.75. All right. Likewise, you can solve this one as well. Okay. It's going to be the same thing. Do you want me to solve it or will it be okay? Let me know if you want to solve.
Clear,
We can
ma'am.
solve this together. Yeah. Say that again.
I'm clear, Abhi.
Clear? Hai? Okay, fine. Good. Okay. Now, just like that, we have this thing here. Okay. So this is going to be nothing but just an expression. So let's try this one first. So this is going to be the original thing. So that's 2 divided by when you're fixing for a certain value of y that we just have here, this one. So that's going to be 2y, right? So it's going to be 1 by y. Okay. And likewise, this one, it's going to be 2 upon 2 into 1 minus x. That's 1 upon 1 minus x. Right? So we have had the marginal probability, we have had the marginal cumulative probability, or just cumulative probability, and we have had the conditional probabilities for continuous random variable also. Last two. Okay. So what was this thing telling us or asking? So this was saying that what is the distribution, the sort of the probability to get X when you're fixing a certain value of Y. Okay. So whenever we fixed this value of Y, right? So imagine this Y was a certain value, a particular value. Y was 1, Y was 0.5, whatever that value of Y was. This is what we got. So this is what we fixed. And what is the probability of X? So again, what we talked about for discrete ones, numerator is going to be the joint probability and denominator is going to be the marginal probability. So joint probability here was 2. You just need to write that expression again and divide it by this thing, the cumulative probability of Y, right? That's going to be 2Y. And whatever that value of Y was, whatever value of Y you fix. So here in the question, it's not given, but maybe it could have been given that it's going to be 0.75. So if it was 0.75, you just put that value right here. Likewise, this is the opposite. So conditional probability of getting Y when you're fixing the certain value of X. So the first part, you are calculating it for all X. Sorry, to get a particular value of X, you're doing it for all Y's. You get this marginal probability, and then that's divided by the joint probability. That divides the joint probability. Did I confuse you? Is it clear? Confused? Okay. So if you remember, so do you think the color scheme is going to help you? Should I explain it in terms of the color scheme, the formula, first of all? Yeah, okay. So if you, so you were familiar, you were able to appreciate this one, right? The one for the discrete random variable. We calculate the marginal probability, right? So this was in terms of X, this one was in terms of Y, and then the conditional probability here states that Y is a certain value. So when you're saying Y is a certain value, you're not talking about any value of X. So you summed it up over the whole range of X, which is what gave you this green thing here, right? So for the pink expression, the denominator is green and the numerator is your original expression. This is what we did here as well, right? For the pink expression, the denominator here is the one in green. So 6 plus 3y by 22. And the numerator here is your original expression. So that's exactly what we're doing here as well. Okay. So for the pink expression, the denominator is the green one. What was the green thing? It was the marginal distribution in terms of Y, because we are taking all values of X throughout the whole range. This is what we did here, right? The whole range of X. And that became the denominator, and the numerator was your original expression. So this was 2 here, right? So 2 divided by 2y, that's 1 by y. Yeah.
Joint PDF and marginal PDF are same, ma'am. F of X and Fx y of X of y, X comma y are same or not?
No. This is joint probability and this is marginal probability.
But you have written there F of X comma, that is X comma y must come, I think. Here, the same line.
This one?
No.
This
That two. First line.
This thing 2.
Ma'am, first line.
This thing.
Yeah. Before that,
oh, sorry. Okay, I'm very sorry.
F
Yeah.
of X,
No, this is wrong. Sorry.
F of X comma
I
y.
was just copy pasting something. So,
F of X
okay.
comma y.
Yeah. That is extra. When I was adding my PowerPoint to it.
Yeah, okay.
So something, but thanks for pointing out. Yeah, I'll just remove this. Yeah, right. Now it should be okay.
Okay.
Yep.
That
okay.
is just a conditional probability definition only, this one. Yeah.
Yep. Okay, perfect. Okay. Are we good to go to the next slide?
Yes, ma'am.
Okay, fine. So again, for continuous random variables also, we can calculate the expectations. Okay. So I'll come to these two expressions in a minute, but before that, see this example. So again, when you want to calculate the same thing, right? I'm writing it in the same way. So the expression inside this expectation thing, it's written the same way as you write the conditional probability. So it's sort of easier to remember that you need to use the respective conditional probability, right? So this one that you use here and multiply it by x, right? So because it is in terms of x and this is in terms of x, everything is in terms of x. So you're going to integrate x for the ranges 0 to until the particular value of y that you are talking about, whatever value of y was fixed. Okay. So, yeah, let's try to solve this as well. I'll come up to the upper two expressions in which after solving this. So let's solve this one first. So again, so this is how expectation is written, right? The random variable into the corresponding probability. For
Ma'am, doubt.
Yes.
The variable here in the definition of second line, first line, that phi of y equal to expectation of
I
g of
will
x.
come to phi in just a minute. Abhi, I'm not talking about this. I'm
I have
directly
one doubt. I have one doubt there. Instead of suppose g of x comma y, if you have instead of g of x comma y, suppose we are having x means and L minus into x, fx given y.
Not following. Wait. Go slow.
Ma'am, instead of g of x comma y, replace x.
It's the same thing. It's the same thing. Yes.
Same thing. Okay. But instead of that fx given y equal to y, is there no? There is a problem. Instead of x, we replaced g of x comma y. So that here also fx, no? There also you have to replace, no?
I'm not following. So instead of what, I need to write what?
Yeah, that point only. X, no, fx given y equal to y.
This one.
Yeah. That instead of x, we have function, no, g of x comma y. We have to replace that one, you know.
So, okay, give me 2 minutes. I will solve this first, and then we will come on to this thing.
Okay, no problem.
So, first of all, what we want to do here. So, I don't have the simple thing here, the expectation of x only, like we did for this one. Expectation of x, expectation of y, but it's going to be the same thing. So I'm directly jumping onto this thing here. So what we are doing is the random variable into the probability of getting this expression in the first place. Right? This is what is there. So it's exactly the same thing. So take a look at the color scheme. It will help you a little bit. Right? So what value we got from here? It was 1 by y. Right? What happened? Yeah. So here is going to be x 1 by y dx, and we are going to integrate it from some range. So now typically for these, value of y should be fixed, right? But let's say here, so y is not a random variable here. Y is not a variable here. Let's say y could be 0.1, y could be 0.5. It could be any value. Okay. So whatever that value was, we'll take it out of the integral. And here we are going to integrate it until that value of y, right? So here, if you remember, the lowest value y could take was 0, right? So it was between 0 up to y. It's going to be x dx. We're integrating from 0 to y. So y is a constant here, right? So x dx gives you x square by 2. going to be x square by from 0 to y. So it's going to be y square by 2 divided by y. So it's going to be y by 2. This thing. Did this make sense?
Okay, ma'am.
Yeah. Likewise, you can do the other one also. So it's going to be, so if you remember this one, the range of x, that's all, that's between, yeah. So that can also be, why did I write 1 to x? Oh, sorry, we are integrating y, right, here. So it's going to be y, and the one that we got here was 1 by 1 minus x. And the integration is going to be, so the integration in terms of y, it's going to be between x and 1. So it's going to be x and 1. This is what values y can take. Now x is a fixed value, right? You see this x is equal to x. This means x is a fixed value here. So you take it out of the integral. You do a x to 1 y dy. That's going to give you again y square by 2. Right? So 1 by 2 into 1 minus x y square 1 and x. Please tell me if you're not following, okay? I might be skipping some steps. I have absolutely no problem going through it slowly, but you have to tell me.
Y square by 2, no?
The 2 I've taken here.
Okay.
2 is a constant, no? So I've just taken it outside.
1 minus
1 minus x was here. This constant. We calculated this thing. Oh, wait, yeah. This thing. 1 upon 1 minus x. Remember?
that is okay, ma'am. But here integration, yeah, y square by 2 integration, substituting upper limit 1 square minus 1 by 2 take outside, 1 square minus x square,
I
no?
will solve it. I am still solving it.
A plus b into a minus b will come, no? 1 plus x will come.
Wait. I'm solving. Wait.
Okay.
So it's going to be 1 minus x square.
Yeah.
Right? 2. 1 minus
2 1
x.
minus. Okay.
So you can do that. So 1 plus x divided by 2.
Yeah. This is the answer.
Cool. Good. Okay.
Yeah.
All right. So now we'll come off to these expressions. So now, as you rightly pointed out, instead of gxy, I could have just written x. If I just write x or if I just write y, then that is also an expression in itself, right? X itself is an expression. It does not have y in it. Y is also an expression. It does not have x in it, but it's an expression. So this just indicates that this formula is valid for any expression in terms of x and y. You can fit in any expression and you'll still, what you get is the expectation of that function, whatever that function is. When you are satisfying a certain criteria that you're fixing a value of y and you're interested in all possible values of x, right? Just as what we are doing in this case.
Okay, ma'am. You just mentioned the top unconditional expectation or a conditional expectation. What is the difference between conditional and unconditional expectation? We have seen now so far only conditional distribution, conditional expectation. Here we are going to see unconditional or just conditional expectation.
So this one is all conditional expectation, right?
And bottom, I think.
Bottom is
yeah,
also conditional expression, conditional expectations. If you now here, if you take the expectation of this expression on its own, then you'll still get this expression back, right? Wait, I might be mixing something. Unconditional expectation, I'll have to check. Maybe I don't think I've explicitly mentioned on the slide. If we get time at the end of today's session, I'll confirm. Otherwise, we'll discuss this in the next lecture.
Okay, ma'am.
I might have missed it in the presentation, but please remind me at the end of the session. I'll try to see if we have time. Otherwise, next class definitely.
Okay, okay.
Okay. Thanks for pointing it out. Okay, so we are done with some basic expressions for discrete and continuous random variables. We'll have marginal probabilities, we'll have conditional probabilities, we'll have expectations, and we can also have something like a cumulative probabilities, which we have seen specifically in terms of continuous ones, but it also makes sense for discretes. Okay. Now, with that, we move on to second part. So we have seen variance, right? You remember we had calculated variance in the initial weeks, and there was a certain expression that we used to calculate variance. If you remember, it was in terms of the expectation of x and the expectation of x square, right? So expectation of x square minus square of the expectation of x. That was the formula for variance. So in variance, what we are seeing, what we are more interested in is how different are the values. So there's just one random variable x. So how different are the random variables from the mean, right? So if you see this inner expression here, so x minus the expectation of x. So how different are the values x from its mean? Likewise, how different are the values of y from its mean? You multiply them and you find the expectation of that. So this is what covariance is, how covariance is defined. You solve this. So again, it's a simple open the brackets. So it's going to be xy minus this into this plus this into this and all that. The steps are written here. Okay. Then you find an expectation of each of these terms. So expectation of xy, you write it as it is. Expectation of the expectation of x. So this term here, it's still the expectation of x, right? Here it's going to be expectation of y. This is also going to be a similar expression, and this is also the same thing, right? So let's say you can cancel any two of these. So you get expectation of xy minus expectation of x into expectation of y. Now, just to double check if this is the right formula, instead of y, you write x. So it's going to be expectation of x square minus expectation of x, expectation of x. So you get the same value. So covariance of x comma x is actually variance of x. You're comparing x with itself, right? So which gives you, just give me a minute. Yeah. So comparing x with itself gives you variance. Comparing x with y gives you covariance. And this is one way of doing it in terms of the expectation, or this thing that we have written inside, it's just a slightly different way. This is how you typically solve it for discrete random variables. So again, what you're doing is you're seeing how different each of the values are from their mean for both x and y. You're multiplying them and you're dividing it by n. By n because that's how many observations you have, right? So do both of these formulas make sense?
Yes, ma'am.
Okay. Right. And the other thing which we will see a little later when we take a quick demo in R, if you remember, we had discussed something sort of a correction that's done when you have sample versus population. So when you're doing population, which means you have a very large size, large number of observations that you're looking at, you divide it by n. But when you're doing a sample is normally going to be a very small population, right? That's going to be a small number. Even if it's 1,000, it's not the entire population. So there was a certain variability in choosing the sample itself. So covariance or variance, that should show that it's a sample. So ideally, what happens is the denominator is even smaller. Like smaller denominator gives you a larger value of variance, right? So which is why in terms of samples, the denominator is normally n minus 1. Okay, but and that n minus 1 is what the value in R is. So R takes n minus 1 as the denominator when it's doing the calculations. But here, for the purpose of the course, and we are assuming sample is equal to population, we are not complicating things. So we want to keep the denominator as n, right? So again, so what R does, it has 1 minus n as the denominator, some expression. So whatever, let's say some expression ABCD is there, you're dividing something by n minus 1. This is your expression. But what you actually want is this. Okay, this is what R does. This is what we are interested in. So what you do, you multiply it by n minus 1 and you divide it by n. When you do that, you get this thing. Simple. These two values get cut. So what you get is the new covariance. It's going to be a slightly smaller value, but that's what we'll say. That's what we need. So just a word of caution, use this funda in your assignment. Okay, whatever value R gives, you multiply it by n minus 1 and you divide it by n. N is the number of observations. Okay, and here you can see X and Y have the same number of observations. It's a paired data. Okay, unlike where you had in terms of the in terms of the joint distributions and all. So covariance you can only find when you have the same number. They have to be paired. Corresponding to each value of X, there should be another Y. Okay. All right. Another thing about covariance is here we are what we are saying. So, okay, we talked about the formula, but what does covariance show? That how different X and Y are. Okay. And mostly we are talking about the trend. And what trend? We're talking about them following a straight line. So a straight line it can be a horizontal straight line. It can be a vertical straight line. It can be an upward straight line. It can be a downward straight line. Okay, we are talking about broadly 4 kinds of lines. So, a vertical line does not make sense. Okay. It would be like the slope is infinity. So we don't go into those cases. So we are just talking about 3 cases. Slope is 0. Slope is positive when you have an increasing line. Slope is negative when you have a decreasing line. So those slopes, those are actually in a way somewhat indicative of the covariance. So 0 is mainly telling you that there is no trend. So we can take a look at 3 types of distributions. So let's say if this is what it's there, right? Now, here what we are doing is, so let's say if it looked like this, you can fit a horizontal straight line, you can fit a vertical straight line. But what we do is fit a horizontal straight line to it. Okay. Then if you have this sort of a data, you'll fit a vertical line. And if you have this sort of a data, you'll fit an upward line and a downward line, right? So this is 0, this is showing positive, this is some negative value. Okay. And 0 is telling you that there's no relation between X and Y, they're independent. So when they're independent, yeah, so in terms of expectation, in terms of probability, so we know in terms of probability, what holds, right? Probability of X comma Y is equal to probability X into probability of Y. But in terms of expectation also, this thing makes sense, right? So this value is equal to this value. So you get covariance is 0, right? It's a corollary of the expression itself. All right. But now I have a few questions for you. Okay. Before we go to the questions, there are some more things. So there's something called a covariance matrix. We're not talking too much about how this is going to be useful. It will come up in some of the upcoming lectures a little bit, but we'll see to it when it comes. So again, nothing, it's just that So you have a 2 by 2 matrix. The diagonal is always the elements 1, 1, 2, 2, 3, 3, like that. The non-diagonal elements are going to be your pairwise covariances. So covariance xy and covariance yx is the same thing. Okay, it's a commutative property. And the diagonal elements are going to be the covariance of that variable itself. Okay. Would you like to construct a 3 by 3 covariance matrix? Let's say if we have x, y, and z. So we are basically going to have 9 elements here, right? So let's say this is going to be variance x. This is going to be variance of y. This is going to be variance of z. Can you think how are you going to fill the other elements?
Variance xy,
Here. So
variance
variance
xz,
xy. This one,
xz, variance xz,
x and z. So I'm just writing this here. Okay. This one,
yz,
yz. Okay. And likewise, you can fill it here also. This is going to be
X,
xy,
zx, or
xz.
xx,
Yep. And this is
zy,
going to be
zy.
yz. Yep. Perfect. Right? So you can build as much. This is useful in a lot of slightly complicated things. So if you've heard about dimensionality reduction, I'm just throwing words right now, but it's a very helpful process. Like, so it has its own uses. So in things like that, the covariance matrix has its use, but not discussing any of that right now. Okay. And then this one, yeah, covariance of
Self.
xx is equal to the variance of x. When we have two numbers, so when we have like covariance of x and x is multiplied by something and another term that's also multiplied by something, then that covariance, so we have seen previously also, when you have some numbers added, your graph is just going to shift left and right. The variances don't change. But when the random variable is multiplied or divided by a certain number, then the variance has a change. So whatever that number was that was multiplied or divided to your random variable, that shows up in the change. Okay, in the covariance. And when you're talking about variance of a new random variable, which is the sum or difference of two random variables, then it's going to be the sum of their variances, and their covariance, double of their covariance can be added or subtracted depending on whether the random variables were added or subtracted. Again, this is just a formula. You'll have to remember it. I cannot give you an example right now as such. I don't think I have an example for this particular thing, but yeah, this is what was discussed. Now I think I have a few questions for you. So, okay. So the answer is also below, but let's see. So the two random variables that we're talking about, x and y, they can have any units, right? When you have normally the examples that we've seen so far, we've never considered units of any expression of anything, right? But let's say when you do have some formula, you're measuring certain things, x and y could be some measurements, they can have their own units. Okay. So let's say in one case, they have units kg and meters. In some other case, somebody else is doing it, they are calculating in terms of grams and centimeters. Okay. So now the unit of covariance, so the formula that was here, you're multiplying x and y basically, right? So the unit of covariance is a multiplication of the units of x and y. So in this case, it's going to be kg into meters. In the other case, it's going to be gram into centimeter. So definitely the value is changing, right? The magnitude is changing. Whether you can derive one from the other, because you change kg to grams and meter to centimeter, you can get the other value. That's true. But then what it means is that absolute value 1000, right? So if I say, I give you three cases. So I say 1000 kg meters. I give you 1000 gram centimeter, and I give you, let's say, 1003, and let's say gram centimeter. Okay. So now this expression and this expression is actually the same thing. But by magnitude, this 1000 and this 1000 look similar. Okay. Right now, all the examples that we have seen so far, even though we did not calculate covariance, but we have only been talking about values, right? 1 by y, 1 by 2, 0.7, whatever. So it is not just enough to look at magnitudes. Maybe you'll need to look at units also. But then let's say if you're talking about something completely different, we're talking about, let's say, 1000 liter into whatever, let's say liter into grams. So this is, again, this is very, very different now. How do you compare this? It's not at all comparable, right? So so covariance that we just saw right now, since it has units associated with it, and those units depend on what the question was, it is not enough. Okay, that value is not indicating anything. So we need to do two things. One is we need to remove the units, no gram, no centimeter, nothing. Also, we should do away with the magnitude and we should bring it down into a certain range. So the range that we would now bring it down is between -1 and 1. And how do we do both the things together? We divide the covariance by variance of x and variance of y. You multiply it and then you take a root. So remember, variance of x would have square the units of x, right? So it's going to be something like this. Let's say for the first example, unit here is kg and meters. Here it's kg square, meter square, and you take the root. So you get no unit. And also you'll see that this value, we'll call it small r, it's going to be between 1 and -1. So that's called the correlation coefficient or just correlation value. Again, there are different formulas. We are talking about the most basic one because we were trying here for a linear relation between these two. So for linear relation, you always calculate it by this formula, and it gives you the Pearson correlation coefficient. There would be cases where x and y, they are not linear, right? So for example, maybe they have this sort of a trend somewhere, right? So you can't fix a straight line. You'd rather have to fix a curved line like this. A curved line would be better. You can fit a straight line, but that's not correct. All right. So, so when correlation coefficient gives you 0, it does not automatically mean that x and y are not related. It just means that they are not linearly related. They may have some other relation. So it's often a good practice to try to plot this first, plot x and y, and then decide if you want to fit a straight line or not. If you want to fit a straight line, then you go for this Pearson correlation coefficient. Otherwise, you don't calculate Pearson correlation coefficient because it will give you a wrong value. Okay. Did this make sense? Because this is what we had to discuss. Now we don't have a lot of time. So I think there are just 3 or 4 questions, but we need to discuss these questions because they are important for solving the assignment. And like we had, I think even for the last week or like 2 weeks amongst the last 3 weeks, we have not been able to discuss the assignments at length. We might do that at the end of the session, at the end of the whole session, right? After 12 weeks. So for now, in the next 20-30 minutes, we will take a look at these more questions because they are important. They are a bit tricky. Some things are important, some difficult formulas of integration. So let's solve that. If you haven't already taken a pen and paper with you, it'll be nice if you have one. Otherwise, anyways, I'm solving these, but it'll be good if we can solve along. And do remain as interactive as you've been so far. Okay, fine. So let's solve this. Okay, yeah, fine. So we'll start off with the first one. So again, we've been given an expression. It's a bivariate distribution, both x and y, and we have been given the values that x and y accepts. And then we are asked to calculate certain probabilities. So whenever you want to calculate probabilities that's less than, more than, you'll integrate, right? For continuous random variables, anyway, we need to integrate, right? Point probabilities don't make sense. So we are going to integrate. So we have two ranges, right? So we'll just write it like this: 2e to the power minus x, e to the power minus 2y, dx and dy. So the inner integration, let's first write it in terms of x. So x takes value 0 and infinity. And x here we are talking about greater than 1. So here x is going to be 1 to infinity. This is how you will write. And the outer one we'll write in terms of y. So y can also take 0 and infinity, but we are only interested in less than 1 values. So y is going to be from 0 until 1. So this is the first part. So you have created the integral that you want to solve. Now we solve it. Now the first part here, the one important and easy part for this sort of a question is, now x and y are not related to each other. You can, so when you're doing a double integration, the one thing you need to be cautious about is that is either of the random variables dependent on the other. So we'll see that in the second part where x and y, they have this relation here. But otherwise, in this case, they're both independent. So what we can, independent, yes. They're not written in terms of the other, right? X has its own value between 1 and infinity. Y has its own value between 0 and 1. They're not connected. One does not affect the other. So we'll write again this 0 to 1. So when we are solving dx, this y expression can be considered to be a constant. So 2 is also a constant. E to the power minus 2y is also a constant. So we'll write x is equal to 1 to infinity, e to the power minus x dx. And once we solve this, we'll solve the dy thing here. Okay. So I'm going slowly. So bear with me. I don't want to make any mistakes also, and I just wanted to be clear. So this is there, 0 to 1, 2, e to the power minus 2y. Now, e to the power x, the integration is e to the power x. And whatever the value is, whatever the power is, it comes as 1 upon. So here it's minus 1.
By
E to the power ex. So
by
it's going to
a.
be minus.
Yeah.
Right? So it's going to be minus e to the power minus x. Right? And we are integrating this, like the limits are going to be 1 and infinity. Dy. Again, the same expression here. So now if you see this, so minus x means 1 upon e. 1 upon e to the power x. So let me solve this here. Minus x, that is equal to minus 1 upon e to the power x. Now, when x is equal to infinity, this is equal to minus 1 upon a very large number. So it's almost 0, right? And when x is equal to 1, so it's going to be just 1, right? So it's going to be minus e. So minus e, that's going to give you plus e, right? Does that make sense? Yeah, should be okay. So this is going to be 2 to the power e to the power minus 1. Integration e to the power minus 2y from 0 to 1 dy. Did you understand how we got from this point to this point? Right? We're solving, just putting in the limits. Okay, now again, so 2 e to the power minus 1. Now we are integrating this thing. So this comes in the denominator, minus 2 comes in the denominator. It's going to be minus e to the power minus 2y upon 2. Now we are integrating from 0 to 1. So again, let's put this 2 out. So it gets cancelled. This is going to be e to the power minus 1. Here you'll put 1. So it's going to be e to the power minus 2. And then when you put 0, it's going to be just 1. Right? So it's going to be 1 minus e to the power minus 2. Anything to the power 0 gives you 1. And this was minus e, like this. I mean, there's a lot of minus signs involved. Try to solve it. Like, take into account all the 2, 3 minus signs. You will get this. Okay. So here we have evaluated the first expression. So now let's go for the second one. Okay. So the second one, we'll also write in terms of both x and y. Yeah, okay. Now, x is less than y. So what we are going to do is, so x goes from 0 to y. Again, we have the same expression. Please let me know in case you are not following anything. And y goes from 0 to infinity. Now, tell me, which of the two integrations should we solve first and why? There's one for x, there's one for y. Now, this expression, the one in red, you can do it the other way also. You can first solve for y and then solve for x. You'll still get the same answer. You give it a try, just to be sure. But this expression, since x and y have some relation between them, you cannot do it for all. You cannot do it in either way.
Ma'am, how we are setting the limits in this case?
Okay, so we have two integrations always, x and y, right? So here the question says x is less than y. So x goes from 0 to infinity, but we've also put an upper bound, which is y. So the limit of x here is going to be between 0 and y. But y did not have any limits. You don't set it for 0 to x also. You can't do it left and right. This expression needs to be written at only one of the two cases. So y limit stays whatever it is.
Okay.
0 to infinity.
Thank you, ma'am.
Right? X will be first, right? So this integration, the inner one that we've already written inside, that's going to be the first one. But for this, y can be considered the constant. So again, we'll do the same thing. 0 to infinity, 2 e to the power minus 2y. We'll get e to the power minus x. 0 to y dx dy. And then when you solve it, you'll get again this thing, 1 minus e, like minus e to the power minus x. You'll put y here. So it's going to be minus e to the power minus y. Minus minus plus e to the power 0. That's 1. Okay. So let me write it. Anyway, it's okay. This thing, integration from 0 to infinity, 2 e to the power minus y minus 2y dy. We can solve this a little better because now both expressions look very similar. So this 2 can anyway, let's solve it here. So this 2 can go anyway here.
I think we have to use marginal PDF of x. We are having only x, no, we should not apply that y. I think.
Probability it's
Third one I am asking.
let's
no
come
y,
to the
no.
third one whenever we come to the third one. We are still solving the second one.
Okay. Sorry.
Yep, okay. But you think about it, what point you have raised. Here also, even though we have written y here, but the expression is only in terms of x. But we are still integrating y for the whole range. So this is in terms of your marginal probability. So you're integrating over the whole range of y. There's no limit to y, so you're doing it for the whole thing. But we'll do it explicitly once we come to that. So this 2 comes here. This is going to be, so this is going to be minus, yeah, e to the power minus 3y plus e to the power minus 2y. And it's going to be dy, right? Yeah, it should be doable. 0 to infinity. So this 2 stays out. This is going to be minus 3, goes in the denominator. So it's going to be e to the power minus 3y by 3. Here the limits are going to be between 0 and infinity. And plus, this is going to be actually minus here. Minus, this is going to be e to the power minus 2y upon 2. 0 to infinity. This whole thing right here. Tell me if I'm wrong. I have not done integration in a very long time. I only practiced it for the last couple of weeks for these questions. Okay. So again, when you put infinity, anything, so in the denominator is e to the power infinities. It's a very small number, that becomes 0. So you have a minus when you put 0 here. So when you put 0, everything here becomes 1, right? So it's going to be minus 1 by 3. It's going to be plus 1 by 2 into 2. So it's going to be 2. It's going to be 6. This is going to be minus 2 plus 3. So 3 minus 2, that's 1. 2 by 6, that's equal to 1 by 3. Okay, this is the second expression. Now for the third expression, let me add a new slide here. Maybe we can put this one here. Okay. All right. So let's take third color, green. So x less than c. So what we are going to do here, again, it's going to be a double integration. Y is going to be for the whole range, but x is only going to be the range for c, until c. So 2 e to the power minus x, e to the power minus 2y, dx dy. I don't know if we'll have time to solve this in detail. Let me go through the next few questions a little quickly. I need to show you some important things. I don't want to exceed the time. But if you solve this, the answer you should get is 1 minus e to the power minus c. Let me know in case you don't get this. Okay. But you should get it. I've tried it. It's working. Okay. So, but let's take a look at this question again. So again, this is the joint probability. Here x and y are between, they are independent, but they are between 0 and 1, both of them. You can calculate the marginal probabilities and the conditional probabilities. So when you calculate the marginal probability, so this one, let's say, use the black pen. Okay, so when you calculate this, so here you're going to integrate over the range of y. Okay, remember? That's what the marginal probability of x means. So the range of y, that's going to be x plus y dy, right? So x is a constant here, right? We are not doing anything for x. So x comes out, it's going to be 0 to 1 dy plus y dy, 0 to 1, right? So this y is going to be y, 1 minus 0, so it's just going to be x. Yep. Half. Did you say half?
X.
Yep. And when you solve this, it's going to be y square by 2. So 1 by 2 comes out, y becomes 1 minus 0. So that's going to be 1 by 2. Okay.
Ma'am, how we set the limits here?
Okay. So this is marginal probability of x, right? What does marginal probability of x means? That we are integrating over the whole range of y. No y in the final expression. So the whole range of y, this is between 0 and 1.
Okay.
And so just that expression into dy, like not into, integrating over y,
Okay. Okay.
right? Same thing you'll do here. Since it's a very symmetric looking distribution, this one would give you y plus half. Same thing, same solution.
Ma'am, for x, again the limit will be 0 to 1.
Yep,
In
yep,
this.
yep, yep. Same thing. Just replace x and y in this expression. It's the same
Okay.
same thing. Because you see, it's very, all things are independent. It's very symmetric looking thing. You know?
Okay.
So that's going to be the second expression here. Now this thing right here, conditional probability. So if you remember the formula, it's a numerator by denominator sort of a thing, right? Numerator is the joint probability, which is given in your question, x plus y, and denominator is y when you're fixing a certain value. So in terms of y, so this green thing here, which is y plus half, right? Likewise, this one, x plus y, and then for a certain value of x. So,
X plus half. X plus half.
yep. Yes, any questions? Now, if you want to check if x and y are independent, you can just compare their marginal probabilities and you see if you multiply these marginal probabilities, do you get the original back? Yeah, sorry. Right? So if you multiply x plus half and y plus half, do you get x plus y? No. Right? You don't get x plus y back. So x plus half into y plus half, that is not equal to x plus y. So we'll say they are not independent. Right? Now again, this thing, it's like what we did in the previous question, right? This first part. So it's going to be a double integration. Y is 0.4 to 0.7. X is 0.5 to 0.8. You have x plus y, dx dy, right? So now when you're solving dx, so this integration 0.4 to 0.7 goes here. You'll have sorry, 0.5, 0.8 dx plus y 0.5, 0.8 dx here like this, right? So what I'm doing here is I'm just calculating dx for now, the inner integration, but for both the terms, for x and y. So x dx and only dx with y as a constant outside. So this is going to give me x squared by 2 with these limits, plus this is going to give me x with these limits. Then again, I get two values. I'll solve them for the second integration. I am running out of time, so I'm not solving this whole thing, but you will get the answer. It's going to be 0.1080 or 0.108. Okay. If in case you're not able to solve this or you want me to solve it, we'll take it in one of the upcoming classes whenever we get time. Hopefully we get time in some of them, but this should be doable. Okay. Fine. Now this is an important question, and it took me a while to figure this out. Again, same question. You have a joint probability distribution given to you. This one's very complicated looking. And the ranges are also independent. They're both x and y vary between 0 and infinity. Now you want to check if they are independent. So same thing what you did in the last one. You want to calculate their marginal probabilities and see if multiplying them gives you the same original joint probability back. So the marginal probability, so let's calculate one of them for now. Okay. So did you say something? Okay, give me a minute. I'll just solve this quickly because I really want to show this to you before we end the class. Okay. So the marginal probability here. So let's say we are integrating for the ranges of y. So y is equal to 0 to infinity. It's going to be 4x y e to the power minus x square plus y square dy, right? This is what it's going to be. So let's rearrange it a little bit. Whatever the constant terms are, we'll take this out. So 4 is constant, x is constant. Now, this thing for this, you remember, it's like this, right? And what does this indicate? This is like 1 upon e to the power x square plus y square. This is similar to 1 upon e to the power x square into e to the power y square. So you can split these two things, right? So e to the power minus x square comes outside. Now you integrate from 0 to infinity y e to the power minus y square dy. This is what your integration is. Okay. Now I have a certain trick written here. Otherwise, it becomes very complicated to solve. So the trick here is when it's x e to the power minus x square dx or y, x or y, same thing. When it's this sort of a looking formula and your ranges are a and b, then the integration of that is going to be basically, you think about it, you're changing the integration to look like e to the power u, right? And e to the power u du gives you eu back. And this u is going to have the limits minus a square and minus b square. So what is happening here is this integration is actually going to give you e to the power u, where your limits are minus of 0 square. So minus 0 square is still 0. Minus of infinity square is minus infinity, right? Let me know if this is not clear. So this is the expression y e to the power minus y square dy. Okay. This becomes a new version. It's like EU, where your limits from a, they become minus a square, and from b, they become minus b square. So a here for us was 0. So minus a square minus 0 square, that's 0. And infinity changes to minus infinity because minus infinity square is still infinity, right? So this is there. Now you solve this. 4x e to the power minus x square. E to the power minus of infinity, that's still 0. Minus e to the power 1, that's 1. Right? This is giving you minus 4x e to the power minus x square. So this is your this part. Okay. Oh,
Just
there's going to
replace
be
dy.
there's going to be a half somewhere. I missed it. This half is going to be there. Yeah. So it's actually going to be 2. I'll edit this when I'm sending you the yeah, maybe I'll just do it right now. There was too many things to take care of. I think there's going to be a, how do we write this expression? 1 by 2. Perfect. This looks good. Okay, right. So this is what your expression of fx, the marginal probability of x is. And you solve it the same way. You get minus 2y e to the power minus y square for this one. Now you multiply these two terms. Do you get the original back?
Yes,
Yes or
ma'am.
no?
Yes, yes.
Yes. Right? So you can say that they are independent. Okay. And I think I just have one final question. This is a very similar question to the one that's there in your assignment. So X, Y, and Z, they are random variables with 3 different means and their respective variances, and all the pairwise covariances are also given. What's the covariance of 2 new random variables U and V, which are some combinations of X and Y, X, Y, and Z? Okay. So now we want to calculate the covariance of U and V, which means we want to calculate the covariance of X plus 3Y plus 3Z and 2X minus Y minus 4Z, right? So first of all, we need to calculate some values. So we have the variance of X with us, right? That is 5. We have the variance of Y with us, that is 7. We have the variance of Z with us, that is 4. Now, here we have 2X, right? Okay. Let's solve it a little better way. So we want to calculate the covariance of X comma 2X plus covariance of X comma minus Y. This thing, right? It's a pairwise. We are opening the brackets. I don't think the formula, this one was explicitly talked about in the lectures, or I might have missed it, which is why the question here makes it clearer. Then we want to calculate the covariance of X with minus 4Z plus covariance of 3Y and 2X, or rather you can write it as 2X. Oh, sorry. My fault. Plus covariance of 3Y with 2X plus covariance of 3Y with minus Y plus covariance of 3Y with minus 4Z plus covariance of 3Z, comma, 2X, covariance of 3Z with minus Y, and covariance of 3Z with minus 4Z. Okay. Now, there are going to be 9 values that we calculate, right? So X and 2X. So can you tell me what would be the covariance of X and 2X from the given values? How are you going to find that out? Any idea?
Using variance of X, ma'am, because covariance of X and 2X.
Yep. Yes. So this is going to be, so first of all, the one thing we saw was like when you have 2 expressions and if there's something multiplied here, that gets multiplied to the output. So covariance of X and X is like variance of X, that's 5, and you multiply that by 2. So you get 10, right?
Ma'am.
Then X and minus Y. So X and Y is 2, and you multiply that with minus. So you get minus 2. X and 4Z, like X and minus of 4Z. So X and Z here is minus 4, and you multiply minus 4 to that. So that's going to be plus 16. Are you able to follow this thing?
Yes, ma'am.
Right? Okay, good. Right? Likewise, we'll have 3X and 2Y, like 3Y and 2X. So X and Y here is 2, and you multiply that by 6, so you get 12. Then X and minus Y here, oh, sorry, this one. 3Y and minus Y. So Y is 7, and you multiply that by -3. So that's going to be -21. Yeah, okay. And then you will have y and z giving you 1, and you multiply that by -12, right? 3 and -4. So you get -12 here. And then x and z is going to be -4. So -4 into 6, that's -24, and so on and so forth. Both the things, and then you just sum it up. So now this value can be positive or it can be negative. And since it's covariance, it's not correlation. So it can be, it doesn't have to be between -1 and 1. It can be any value. I don't remember the final answer. So whatever the value is, by solving this, that would be correct. Okay. So I think we've reached the end of time. So you asked me questions 8 and 9, but let's keep it for the next time. If there is, I mean, if you want an urgent reply, maybe you can just put it up on the discussion forum.
Ma'am, ninth problem only doubt because
Yeah.
they have released the solution with the detailed answer, no problem. Answer is no problem. But problem is that 0.841, is not the option for the assignment 7.
Yeah.
Instead of 0.841, can you go through the assignment question,
I've
ma'am?
opened this. Can you see the slide? Can you see this?
This is solution. This is solution. No, this is solution. We are having 0.841. We get the answer. We got the answer, but we go for the assignment. That option is not available.
Oh, okay. Wait. Give me a second.
Yeah.
Mm.
We got the clear solution. No need to explain, ma'am.
Okay. I'm opening this. Week 7 quiz. Oh, okay. This option is incorrect here. Okay.
Yeah.
All right, fine. I will put this up. So assignment 7, question 9. Answer is not there. Right. Okay, fine. I'll tell this to the TAs who are setting up the questions. But also from your end, just put it up in the discussion forum. If you have not already done that, it'll just quicken the process.
Where is the discussion forum, ma'am?
This thing.
In the
where is it? Wait. Logged in. Yeah, Q&A. This thing. You write continue, and then it will take up you to a Google this thing. So some of the people have already put this. We'll get it removed from the evaluation. It's already done. So it will get sorted. Nothing needs to be done. Okay.
It means they will give a mark, ma'am.
So now instead of 15 questions, you will have 14 questions.
But they gave only 93 marks out of 100. All the questions are correct.
Say that again.
Ma'am, I got in the assessment only 93 marks. My answers are correct.
They will remove it from. They have not done it yet. They will do it.
Oh, okay.
They will remove it from the evaluation. So it's out of percentage, you will get 14 out of 14 then. In case it's still not done in 2-3 days, you just put it up again on the discussion forum that how it's going to be done, by when it's going to be done, but it will be done within a week. It should be sorted.
Okay. Thank you.
Okay. All right. So thank you, everybody. And again, apologies for exceeding and not completing all the questions. There were a few confusion here and there. I'll sort that out and upload the slides. But until then, the session is recorded. I'll upload the video. This slide, we were not able to discuss the R thing here, but it's very basic. It's exactly what was discussed in the in the slides in the lectures, right? I'll anyway upload this, but let me know in case something's confusion, if there's some confusion or anything. I'll see you all next Friday then. Okay. So the deadline for this week's assignment is the coming Wednesday, 20th of March, and we'll meet again on 22nd March. All right. Next Friday. All right. So thank you so much for joining in. And good night. Bye-bye.
Oh, thank you.
All right. Bye.